Hi, I'm just going to give you some of the approaches by which we can use transformer-based architectures to address some of the unsupervised text tasks. Even though most of the language models can achieve these unsupervised tasks in the way that they can because of the inherent feature extraction capabilities that they have. What differentiates self-attention architectures is that they learn a lot more nuances of the text on which it is trained on. So let's go into the details. I mean, I'm just going to touch upon how the attention architectures are able to capture such a detailed nuances of the language, and then in the as we go, I'm going to highlight and point out some of the reproducible hacks, I would say, to address the unsupervised tasks using those fine-grained features that these architectures capture. And I'm Venkat, currently working for Ether Labs, and let's get started. Yeah. So yeah, to start with, what are these? I'm just going to give you a heads up on what these self-attention slash transformer architectures are, and then why they're so so hot these days. I would say 2018, late 2017, 18, and then continuing to 2019. There are a lot of, if not by volume, by quality, there are papers that uses these self-attention architectures to address the language tasks. Like to start with GPT, well before Google's BERT, and then comes the BERT, and then Microsoft's MTDNN, and then GPT-2. So all these have an underlying architectural similarity, which means that they use these self-attention architectures instead of the conventional. I mean the 2015-16ish LSTM RNNs for addressing the text tasks. So I mean, what's so different about self-attention architectures is that instead of uh, unlike the sequential RN and LSTM stuff, I mean, these architectures teach for each of the token within the sentence. What it does is it tries to each token tries to attend across multiple adjacent tokens, and see how each of the adjacent tokens are related to itself, right? So say, for example, in this case, on the left, right, on the right hand side, you see it. So what does it represent here is what you can actually visualize. The strength of the color tone here represents that the likelihood of the confidence that it can be is more linked to that token here, because all these language model I mean, all these language model architectures does inherent tokenization the way that they want, and then this is what you get out of the tokenizer. So it represents the animal predominantly. So that makes sense, right? So in the sentence here, the animal didn't cross the street because it was too tired. The street can't be too tired, so it has to be the animal. That's how it disambiguates the language nuances. And then this is the best part about uh, the self-attention architectures. Here, I'm just cheating. I'm kind of, for the sake of visualization, I have just cheated a little bit. So what you can see here is, I'm just showing you the visualization for the fifth layer, and then you can see the second attention head. I'll come into the details later in the later slides, but that's what captures the this kind of behavior of of the sentence or the architecture, wherein the self-attended token actually points out to itself, or or the other tokens that directly refers to this. So which is like in the fifth layer, second attention head. So I'll come to what it means. So this is like I'm not going into the details of how these attention architectures work, because they're pretty complex things to discuss. So that may be, I mean, I'll leave you to this awesome tutorial which explains both the self attention architectures in general, as well as in a different post, the author explains the BERT architecture, which is like a central theme for this discussion. So before that, I think Vaswani et al. From Google has actually published a groundbreaking paper in 2017 on this self-attention architectures. So yeah, and then coming to what this multi-headed attention is. Say for example, I talked about a token being able to look up for what it wants. So what it wants may not necessarily be always itself, it's the representation of itself, like it versus animal here. So it may want to, the language in general may want to look at multiple aspects to make a unifying representation of the sentence. So what multi-attention head does is, this is kind of one attention head that we are looking at. So we can actually initialize multiple attention heads, which will essentially in a very trivial notion, what it does is, each attention head actually looks at particular nuance of the language, and then the more attention heads we have, the variety of features that we can capture using each of the attention head. At the same time, it's a trade-off. So you don't want to have tens of attention heads. So because so there will be a lot of redundancy, and then there will be a lot of ambiguity in feature extraction, or it may get overfitted. So that's all there. So it's an art of choosing the number of attention heads for each layer that you want to look at. So again, this is actually, so when we talk about self-attention architectures, these are multi-layered architectures. So instead of one single layer being either an LSTM cell or a convolution, here it's actually, each layer is a multi-headed attention cell, right? So I'll try to add the just a screenshot of how an attention cell looks like, but this is what it is. So now coming to the specifics. So recently